Welcome to this webinar where we will be showing the capabilities of Flownex for modeling slurry systems. In this video, we will define what a slurry fluid is, where it can be applied, and how to model it in Flownex. In Flownex, a slurry mixture is a mixture of a fluid with suspended, non-soluble particles in it. This fluid will also have a non-Newtonian behavior. Typical applications where slurry modeling will be useful is in the design and maintenance of backfill, ash transport and/or transport systems. To demonstrate how to set up a slurry network, we will model a pipe network where a slurry mixture is to be pumped in a pipeline with a diameter of 100 mm and a length of 100 meters. Firstly, we will begin by creating a new fluid. It is important that we know the properties of the fluid. The datasheet of a slurry mixture can either be in a graphical form or a table. Flownex uses a table as input, and the user will have to create it from the graph if that is the only available information. What you can see here is the graphical user interface of Flownex with a new project already created. To create a slurry mixture, I will first define the solid particles in the Flownex material and fluid database. Because it is a fluid, I will define it under materials and fluids. First, I'll create the particles. It is also good practice to give it an appropriate name so that you can easily find it later on. All the data relevant to the slurries will I put under a folder named Slurry. Now I will create a slurry particle. You will see when you create another fluid, each type of fluid will have its own set of unique inputs that is relevant for what is required in modeling such a fluid. This is the dialog for creating a particle. You'll see that the correct densities and other properties will be required. These data usually come from the supplier, or you will have to get it from material testing. A nice feature in Flownex is that you don't have to create a new fluid every time. For the most common fluids like water, there is already a fluid supplied with Flownex as it is being shipped. Now the final step is to create the slurry mixture. The first part will be the slurry particles, and then we will define the fluid in which it is suspended in. For this case, we are going to be using the water shipped with Flownex. The next step will be to create the network. The slurry theory has been implemented for the pipe and variable speed pump. An explanation of the theory applicable to slurry modeling can be found in the Flownex theory manual. The Flownex library here contains components that can be used to model combustion, containers, heat exchangers, pipes, valves, pumps, fans and compressors. Now we have added a pipe to the drawing canvas. Next we will add the variable speed pump, and you'll see that the dotted fibers will turn into a solid line. This will indicate that the downstream side of the pump is connected to the upstream side of the pipe. Now we can add all the geometrical input data for the pipe, like its length, the inside diameter, as well as the roughness. For this exercise, we will use one of the pump charts already available in Flownex. If you want to use your own pump chart, you can create one in the same place as which we have defined the fluid. Now you can also see that for especially added to the slurry modeling, there is something that is called a derating model. This model is implemented in Flownex as part of the slurry theory to account for any changes in pump performance due to the non-Newtonian slurry fluid being pumped. The final step is to specify the boundaries. At the inlet of the pipe, a pressure of 100 kPa will be specified with the slurry mixture at a temperature of 20 degrees Celsius. Then we will have to specify how much of the mixture consists of water and how much are represented by the slurry particles. At the outlet of the pipe, a pressure of 100 kPa will be specified. Therefore, by using this setup, the pump will calculate the work that has to be done to overcome the system resistance. Careful consideration should be made when considering the type of boundaries that you use. When you place a pressure boundary condition on a node, Flownex will automatically enforce a mass sink or a mass source on that node. Then we will also specify the temperature of the fluid on this node. Then after that, we will specify the mass fraction as well on this node. This is so that Flownex knows how much of the fluid in the inlet is made of the particles and how much will be water. We will add the final boundary at the outlet of the pipe. Please note that all the dotted fibers has now been changed to solid lines. For this simulation, we only want a steady state solution. After pressing the Solver Steady State button, we have to look at the trackbars in the Flow Solver Convergence dialog to see if the convergence criteria has been met. If we are happy, then you can look at the results you are interested in. For this demonstration, we are going to look at the pump power and the pipe pressure drop. Now we're going to solve the steady state condition. Now you can see here below there are blue bars indicating the convergence criteria. The Flownex defaults are usually quite acceptable values to base your criteria on. The user can also customize the drawing canvas with the results he is really interested by dragging and dropping it onto the canvas. As you can see here, we only used a simple network, but when it comes to complex networks, Flownex has a huge advantage, especially when you do stuff like pump sizing or optimizing the system. For more information, please refer to the following links.